Good morning, student friends. And yesterday we have discussed about the pressure chapter and hydrostatic forces, which is very important for gate objective type. We have discussed about different types of pressures, absolute gauge, and also vacuum pressure, and also types of manometers, simple manometers, differential manometers, simple manometers, various types, piezometer, U-tube manometer, single column manometer, inclined single column manometer, and differential manometers, two piezometer manometer, inverted U-tube manometer, U-tube differential manometer, micromanometer, and thereon afterwards hydrostatic forces. We considered three plane surfaces: horizontal plane surface, vertical plane surface, inclined plane surface, and also curved surface, and also practical applications in addition to pressure diagram. Pressure diagram is the graphical method for finding out total pressure force, and center of pressure. And also we have discussed about the applications for dam and also log gates, and we'll go through the objective questions, and we'll also take up the next chapter, that is fluid kinematics today. And general objective questions: water flowing in pumping mains may be treated as, the answer is ideal. The increase of temperature decreases the viscosity of liquid in the previous discussion. Yeah. The other one is 1 cubic meter of air weighs about dash newtons. So the specific gravity of air, specific weight, not gravity, weight, specific weight is 1.225 kg per meter cube, and we can multiply with 9.81 to get in newtons. So 1.225 into 9.81, so which is equal to 12. So the air weight, it is 1.225 kgs, in multiplied by 9.8 will be getting in newtons, so that is 12. Answer is B. So third answer is B. And fourth, the hydrometer. Generally soil mechanics is different. In geological engineering it is between for separation of silt and clay. Hydrometer analysis is a better analysis. That geological is entirely separate. Here you can consider that this is for a specific weight of fluids, liquids. Pick up the wrong statement. Piezometers cannot measure negative pressure. Yes, normally it has advantage, disadvantage here. Gas pressure cannot be obtained, high pressure cannot be obtained. And normal piezometer, if you extend a tight piezometer, one end connect to gauge point, other end open the atmosphere, it may not be possible under normal circumstances, but if you bend it down in the U shape, it can be possible. But straight away not possible. Okay, cannot measure negative pressure. Center of pressure is always below center of gravity. Yes, correct. So center of pressure for vertical plane surface and inclined plane surface always below center of gravity, or at least one case horizontal plane surface center of pressure is equal to center of gravity, same location. And ideal fluid offers no resistance. Absolutely correct. So because when the ideal fluid is set in motion, there will not be any resistance. And the tube in a single tube manometer is inclined to increase accuracy. Absolutely not. So accuracy is entirely different. Accuracy you can get with the help of micromanometer. So whether the column is vertical or inclined doesn't matter particularly about the accuracy. So absolutely D is absolutely wrong, but important. And for measurement of very low pressure of gases, so gas pressure is very low, which combination of fluids? Maybe water and kerosene, because mercury obviously high pressure range, and only other than mercury only we have a C here, water and kerosene. And depth of center of pressure. So for this type of problems. Anyway, we doing gate problems also. Normally, you'll be getting or you should have a concept of pressure diagram. Without pressure diagram, particularly gate examination, mostly with the help of pressure diagram, you can give answers in a short time. So some rectangle, maybe vertical plane surface, the top touches the surface here. If you see here, the top touches the surface of the liquid. So when the top touches the surface of the liquid, the pressure at the top is 0. And if you go down to depth of H, it is WH. So we have a triangular pressure distribution. Triangular pressure distribution for when the surface touches the surface of the liquid. It is a triangular distribution. Then, if it is a triangle, then what is the center of gravity? So the pressure diagram is a triangle, and as you know, the center of gravity of a pressure diagram is center of pressure. You remember our discussion earlier. The center of gravity in general is different from center of pressure. That is different. And when you draw a pressure diagram, if you take a center of gravity of the pressure diagram, that is center of pressure. People may confuse, that's why I am stressing here. Center of gravity and center of pressure, both are different. Center of gravity is the point at which weight acts. Center of pressure is a point at which it is the point of application of total pressure force. But horizontal plane surface, they coincide, and vertical plane surface, obviously center of pressure is below center of gravity. And if you draw a pressure diagram, the CG of the pressure diagram is center of pressure. So for the triangle, the CG from the top is 2/3 H. So from the bottom, the CG, center of gravity for the triangle, the center of gravity from the bottom is H/3, from the top it is 2/3 H. So the answer is A. Yeah, a mercury water manometer indicates a gauge difference of 400 mm, the difference of pressure in meters of water. A mercury water manometer, so the pressure difference is equal to 400 mm. So you can take in meters of water, so convert in meters of water. So here, so whatever the gauge reference, that multiplied by the specific gravity of manometer liquid by specific gravity of water minus 1. So let us say the gauge difference is H. So H into S2 by S1 minus 1. So S2 is specific gravity of manometer liquid, and S1 is, if it is a water, if it is oil, it is oil. So you can take that right away, and if it is a water, you can also take H into S2 minus S1. But more general equation is the gauge reference multiplied by S2 by S1 minus 1. So S2 is 13.6, S1 is 1 minus 1. So the 400 mm multiplied by S2 by S1. So S2 is 13.6, S1 is 1 minus 1. So that is 12.6. So 400 into 12.6. So 400 into 12.6, convert 400, because he has asked in meters of water, 400 in meters. So 400 into 10 power minus 3. So this is 0.4. So 0.4 into 12.6. So that is 5.04. So the answer is convert this in meters, 0.4, and the specific gravity difference 12.6. So 0.4 into 12.6 is 5.04. A barometer, as you know, it is for atmospheric pressure. It is for measuring. At 10, answer is D. So barometer is for measurement of atmospheric pressure. The water is the barometer. Okay, in place of mercury, height of water column, while measuring a pressure of 1.03 kg force per square centimeter. So it is obviously, so the atmospheric pressure is 1.03 kg force per square centimeters, which is also equal to 10.3 meters of water, which is also equal to 760 mm of mercury. So straight away 1.03 is equal to 10.3 meters of water. So 11, answer is A. 12. So vertical gate. So this is the problem on application. So vertical gate, 4 meters by 4 meters, pours water with free surface at the top. So he has asked to find out the movement about the bottom of the gate. Movement about the bottom of the gate. So draw a pressure diagram. So top of the gate, it is 0. And bottom of the gate is WH. So W, you can take So it has gamma is the specific weight here. So y is the specific weight here. In this equation, he has given y is the specific weight. So the bottom, if you take a pressure diagram, at the top it is 0. At the bottom it is gamma h or a specific weight into h. So h is 4 meters. So 4h here and h is the height. So then what is the area of the triangle? So area of the triangle is 4h, 4 gamma into 4 by 2, half ph. So B is pressure, that is gamma h, is here it is yh. So that is the base is 4 times y and height is 4 meters. Then the area of the triangle is half 4y into 4. So that is 8y. Then this is acting, so he has asked you to movement about the bottom of the gate. So force into distance. So it is 10.67 into distance. Distance means the CG of the pressure diagram. It is 2/3 h. From the top it is 2/3 h, and from the bottom is 1/3 h. So 1/3 means 1/3 into h. H is 4. So that is 8y into 4 by 3. So that is, you will be getting 10.67y. 10.67y. So the pressure diagram for this case, top is 0, bottom is WH. In place of W has given y and H is 4. So we have a 4H and the bottom is 4H and the height is 4. So the of BH, the area, so 16 specific weight by 2, that is 8y, and the CG it is acting at 1/3 h from the bottom. So multiplied by that gives the bottom, the moment about the bottom of the gate. So the area multiplied by the CG distance is h by 3, that is 4 by 3, which is equal to 10.67y. And 13, 1.03 kg force per square centimeter pressure is equivalent to. Just now we are discussing. So it is 750 mm of mercury, or 1 bar. 1 bar means barometric pressure. We also see, and sometimes we will be representing 1 atom. 1 atm. So that is also say all the above. So this is equivalent to all the above. 10.3 is correct. 750 mm of mercury, 760, 750. Okay. 1 bar is correct. All the above. And the other one, 14. The center of pressure acts at a depth of dash from the base of the dam. So we have seen the dam. Yeah, we have seen the dam. So the problem is, so he has asked you to find out the center of pressure at depth of, so this is the dam here. So this is the water surface level and this is the H here. He has asked you to find out center of pressure. This is center of pressure, which is at a height of dash from the base of the dam. So this is the base. Some of the students are giving 2/3 h. So 2/3 h is correct when he asks from top of the water surface. So top of the water surface, the pressure force is 2/3 h, and whereas from the bottom it is h by 3. From the bottom it is h by 3. In the earlier discussion also I have mentioned the pressure diagram. So here the pressure is 0. And here the pressure is W times H. So this is W times H. And WH into H by 2, WH square by 2 is pressure. And the distance is H by 3. That's what I discussed earlier. So the answer here is H by 3. Yes. So the center of pressure acts at a depth of H by 3 from the base of the dam. So because the top is pressure is 0 and the bottom is WH. So it acts at a distance of CG of pressure diagram, that is 1/3 h from the bottom. Gauge pressure of 0.5 kg per centimeter square, the absolute pressure is approximately. So gauge pressure has given 0.5 and gauge pressure, again I am repeating, there are two definitions. One is absolute pressure is equal to atmospheric pressure plus gauge pressure. The other one is absolute pressure is equal to atmospheric pressure minus vacuum pressure, both are correct. And for this case, you need to use absolute pressure is equal to atmospheric pressure plus gauge pressure. So gauge pressure has given 0.5 kg per centimeter square. So the atmospheric pressure is 1.03. So 1.03 kg force per centimeter square. So 1.03 is atmospheric pressure and gauge pressure is 0.5. So the expression is 1.53. 1.53. The answer is C. 1.53 kg force per square centimeters. 18th question. Hydrostatic force on a plane immerses the surface of a given area and in a given liquid. For example, take any surface which is immersed in liquid. The force equation is WAX bar. The force for the vertical plane surface is, or anything, horizontal, vertical, it is WAX bar. Area is constant for the surface and specific fluid is constant, only variable is x bar. And the force is proportional to x bar. When more the CG distance, we have more the pressure. So the hydrostatic force is increases. So if you see D, increases with increase in depth of CG. Decreases wrong here, independent wrong here. The area is not only area of immersion is different. And increases with increase in the depth of CG. That is the answer. And this is here, 19. Kerosene flows through a pipe under the pressure of 2.5 kg per centimeter square. The pressure head is. So the pressure head in terms of let us say kerosene. It has given kerosene. You need to remember the kerosene specific gravity is 0.8. 0.8, sometimes oil 0.9, kerosene you can take 0.8. So the head is equal to P by W. So the pressure is 2.5 kg per centimeter square. You can take 2.5 into 10 power 4. 2.5 into 10 power 4 is kg per meter square. You have the pressure here. And pressure head is equal to P by W. W is the specific weight of the kerosene. What is the specific weight of kerosene? So it has specific weight, specific gravity is 0.2, specific weight of kerosene is 800 kg force per meter square. And kerosene specific gravity is 0.8. So specific gravity is 0.8, which is equal to specific weight of the kerosene by specific weight of water. Specific weight of kerosene is equal to specific gravity of the kerosene multiplied by specific weight of water. So 0.8 into 1000. So that is 800 kg force per meter square is the specific weight of kerosene. So we have the pressure here 2.5 into 10 power 4. So 2.5 into 10 power 4 by 800, that is pressure head. So that is equal to 31.25. So 19, the answer is C. The static fluid, the forces dealt in a static fluid or dash forces. Forces dealt in a static fluid or dash forces. No doubt static fluid means you need to consider static pressure. The weight is gravity, dynamic is not necessary. So gravity and static pressure is answer for 20. And 21. If the submerged plane surface is vertical, and touches the surface, then pressure distribution is. If the submerged plane surface is vertical and touches the surface, then pressure distribution is very simple. Top of the surface is touches the water surface. Top of any surface, vertical plane surface is touches the water surface, then pressure distribution is. When the top is touching, so that is 0. Top is 0, and the pressure distribution here is WH for any depth. Basically, there is a triangular distribution. No rectangle, no trapezoid, no parabola. So trapezoid is there if the vertical plane surface is at some depth. Top edge is H1, bottom edge is H2. We can get a trapezoid, but parabolic, rectangular sometimes. If the vertical surface is that is different. Anyway, so the answer here is B. 21 is B. And 22. This is an intelligent question. If the depth of immersion of vertical held circular plane is doubled, then the distance between center of pressure and center of gravity. So center of pressure and center of gravity is entirely different. So center of gravity is always above center of pressure. Center of pressure always below center of gravity. So depth of the impression increases or decreases, that will not affect the distance between center of pressure and center of gravity. Center of pressure and center of gravity distance, if it is doubled or trebled, that will not affect. So the answer here is remains same. The other one, the pressure 10 meters below, the pressure 10 meters below, the free surface of the liquid is 9600 kg per meter square. The specific gravity is. He has not given the specific gravity, but he has mentioned 9600 kg per meter square is the pressure. So the pressure is P is equal to WH, P is equal to WH, P is equal to 9600 and H is 10 meters. P is 9600 and H is 10. P is equal to WH. You can find out W. So W is equal to 9600 by 10. So W is equal to 960 kg per meter cube. When specific weight of the fluid is 960 kg per meter cube, what is the specific gravity? We can straight away give the specific gravity is 0.96. So because you cannot get a specific gravity of 9.6 or 8.6, you can think about 0.86, but it is 96. Obviously, the answer is 0.96. Specific gravity is less than 1. So it is 0.96. 0.96. Only mercury is 13.6. And whereas it is less than 1. Less than 1 we have only 0.86. But the specific, the pressure is 9600 kg per meter square. Obviously, the answer is 0.96. The specific gravity. So we have obtained the specific weight of the fluid is 960 kg per meter cube. So definitely the specific gravity is 0.96. So the position of center of pressure on a plane surface immersed vertically in a static mass of fluid. The position of center of pressure on a plane surface immersed vertically. You need to understand the question itself. Otherwise, within short time, we will have a very short time. You need to be sharp enough, you need to be intelligent enough to understand the question. He is asking the surface is vertical and also mentioned static mass, because this is only for fluid at rest condition. And the center of pressure is always less than, center of pressure is always below center of gravity. This particular question definitely we can expect in GATE. So center of pressure is below center of gravity. Okay. The answer is C. 27. An open tank is open here, contains 1 meter depth of water and 50 centimeter depth of oil or specific gravity 0.8 above it. So open tank, below 1 meter depth of water, above 50 centimeter depth of oil. The intensity pressure at the bottom of the tank. So on the top of the tank, 0 or atmospheric pressure, bottom of the tank. So top we have so because we can convert into 0.5 meter, 50 centimeters depth we can convert into 0.5 meters. So 0.5 meters depth of specific gravity of the liquid 0.8. Oil floats on water here. So bottom water and top, bottom is water, top is oil of 0.5. So 0.5, and if the specific gravity is 0.8, what is the specific weight of the liquid for which specific gravity is 0.8? 0.8 into 1000, 800. So 800 into 0.5, so 0.5 meters. So the pressure is W times H. So the top is, we have a 50 centimeters depth of specific gravity 0.8. 0.8 means specific weight is 800 kg per meter square. Kg per meter cube. And that multiplied by the height 0.5. So 800 into 0.5. So that is 400. So the pressure at the bottom of water oil interface is 800. Again, you have a water here, water 1 meter depth. So tank initially 0.5 meters depth of oil. So for 0.5 meters depth of oil, 0.5 meters, 50 centimeters I have converted to 0.5 meters. So 0.5 into 0.8 into 1000. So that is 400. The pressure due to 0.5 meters depth of the oil or specifically 0.8 at the bottom is 400. Then below that we have a 1 meter water, 1 meter depth water. So 1 meter depth water. So 1 meter depth water means again pressure is equal to W times H. So W is 1000 into H is 1. So that is 1000, this is 400. So we have only 1400. So because this is already 1000 here, it should be more than 1000. So more than 1000 we have only 2 here. So it cannot be 1000 because we have the water here either 1200 or 1400. So obviously 8 into 5 will be getting only 4, not 12. So that's why in simple common sense we can give answer 1400 kg per meter square. So these are all gate questions. Pressure and hydrostatic forces. Gate 1, first question. In the given figure, he has given the, and sometimes the gate questions, it is requires understanding and sharpness and intelligence. Otherwise, you will be wasting so much time on one question, you will be losing more time for other questions to answer. This is very simple. In the given figure, if the pressure of the gas in the bulb A, and this material I have taken from fluid mechanics and Haydn machine, wonderful author, and also ACE material I have taken. I acknowledge them with gratitude. Given figure, if the pressure of the gas in the bulb A is so and so, and it is 50 centimeters Hg. So here this is this H is 50 centimeters here, and atmosphere is no doubt, and then height of the column here. So 50 centimeters of mercury vacuum is the height of rise is only equivalent to same. So height 50 centimeters pressure of the gas is 50 centimeters of mercury means the height of rise is only 50 centimeters. So straight away from 50 centimeters you can take the answer is 50 centimeters. So this answer is B. So you can, if you create a pressure of the gas in bulb A is 50 centimeters of Hg vacuum, then the vacuum will lift 50 centimeters of liquid. H is 50. So straight away you can take this 50 here, not 76. 76 is the atmosphere. Cannot be 26 here, cannot be 126, only 50 here. So question 1 is answer B. A tube manometer with a small quantity of mercury used to measure the static pressure. The pressure is static. This is a U-tube manometer. A and B in a conical section through which incompressible fluid flows. At a particular flow layer, the mercury column appears as shown here. This is the mercury column here. And gravity is 9.81 and the density of mercury is 13,600 kg per meter cube, 13.6 thousand. The flow direction here. So the flow direction is obviously have to be here. Otherwise, you cannot expect mercury somewhere here. If it is B to A, so you can expect mercury here, somewhere here. But if the mercury is somewhere here, so you can expect this is A to B. And simple equation. So we can straight away take PA minus PB. We have a difference here 0.15. 150 mm is equal to 0.15 meters. 0.15 meters. And he has given the specific weight 13,600. 13,600 into 9.81 to convert into SI system. So the 9.81 will be getting in newtons here, kilopascals, kPa. Pascal is Newton per meter square, kilopascals. So the answer is 20 kilopascal. The answer is so you see here A and C. Just observe A and C. So A is even myself I am going for C, but the flow direction is A to B. The flow direction is A to B, and PA minus PB is 20 here. Here PB minus PA is 20 here. A small difference here. So when the flow direction is A to B, when the flow direction is A to B, in other words, the pressure at A is pressure at B. Pressure at A is more than pressure at B. So when the pressure at A is more than pressure at B, so then PA minus PB is equal to 20, not PB minus PA. A small difference here. So flow direction A to B, and straight away 20, we can straight away give 20. It seems we can think about that. We can give C, but a small change here. That is the expert way of setting of experts. So this PA minus PB, obviously as flow is direction A to B, the PA should be more than PB and its value is equal to 20. You may be calculating 20 correct, but if you give a C answer, that is wrong. Its answer is only A. Another simple thinking, slightly thinking oriented question. The pressure gauges here, G1, G2, installed on the system, and here we have atmosphere here, and G2 it has given at 1 bar means atmosphere. So here the pressure is atmosphere. He mentioned that this is 1 bar. 1 bar means barometric pressure. The value of unknown pressure at P, that means he is asking the pressure somewhere here. So pressure in the right side is equal to pressure here plus atmosphere. So the pressure he has given is equal to atmospheric pressure is equal to 1.01, atmospheric pressure is equal to 1.01, and the pressure at G2 is 1 here. Phone ring out. So the pressure here is 1.01 atmospheric pressure, and he has given 1 here. So 1 plus 1.01 is 2.01, the summation of this, and he has given 5. So another important is when you go down, so you are coming down from G to D1. When you are going down, so here at this level, atmosphere and gauge pressure, atmospheric pressure and the pressure here, we can add upon 1.01 plus 1.0, 2.01, that is okay here. And suppose if you are coming down, as you are coming down, this sign should be placed. So here the pressure he has given 5. So 5 plus 2.01 is 7.01. So the answer here is D. The other question. A mercury manometer is used to measure the static pressure at a point in a water pipe as shown in figure. The level difference of mercury into the two limbs is 10 mm. He has asked to gauge pressure. So the mercury difference is 10 mm, and the equation, as I already told you, so the difference of height into S2 by S1 minus 1, earlier discussions. So the convert 10 mm into meters here, 0.010 is into meters here. Specific of the mercury is 13.6 by 1, water minus 1. So this is 12.6 into 0.010. This is equivalent to 0.126 meters of water column. Then he has asked to find out pressure. So this is head. Need to convert this into pressure. So this multiplied by specific weight here. Specific weight here. The specific weight is rho into G here. Rho is 1000 kg per meter cube and G is 9.81. You'll be getting that in Newton per meter cube. So Newton per meter cube by Newton per meter cube into meter. You will be getting Newton per meter square. So 1236 Newton per meter square or 1236 pascals. So 1 pascal is equal to 1 Newton per meter square. So the answer is A. So refer to figure here. The absolute pressure. Number choose number choose number choose So refer to the figure. The absolute pressure of the gas A in the bulb is so write gauge equation here, earlier procedure. So the pressure head at A pressurized at A, HA. This is HA here. And the same liquid is continued up to here. So 10 plus 5 plus 2, 17. 10 plus 5 plus 2, 17. So 17 means 17 centimeters. He has taken in mm. So 170 mm into 1. 170 mm into 1 minus. So this is when you are going down, the sign is positive. So HA plus. Again from here, you reach it here, this stage. Again while you are going up, the sign is negative. So minus. In place of 2, it is 20. The specific of the mercury is 13.6. So 20 into 13.6. And again from here to top, again as you are going up, the sign is negative. So 5 centimeters we have 50. 50 into 1. That is equal to this value. And here the pressure is atmospheric pressure. Atmospheric pressure can take 0 or atmospheric pressure is equal to 760 mm of mercury. So this value, you can simplify this. It asks me to find out absolute. So this is this value here, you can take here. And that divided by 13.6. So the answer is 771.2. Absolute. So this is 771.2. So writing gauge equation here, very simple. 170 into 1. They are coming down, again going up, 20 into 13.6, again going up, 50 into 1, which is equal to atmosphere. So the answer is 771.2 mm of mercury. So this is a siphon problem. Normally the velocity, siphon draws water from the reservoir. This is also siphon problem. I will come to the flows afterwards. But meanwhile, the velocity V is equal to square root of GH. The velocity V, if you use Bernoulli's equation later on in the fluid chapter, we will be explaining that. We will be discussing that in the future. But meanwhile, you can take that the P velocity is equal to square root of 2gh, and h is the head difference here. So here the equation is h2 minus h1, h2 minus h1. So the head is created here. This is h2 and this is h1. This is the this is responsible for creation of h2 minus h1. So here, and this is equal to square root of 2g into h2 minus h1. And we have more discussion on the pipe flow when you go to the flow through pipes. Meanwhile, it is square root 2gh, and whereas h is equal to h2 minus h1. The other gate question, the force F needed to support the liquid of density D and the vessel on the top is? The force F needed to support the liquid of density D and the vessel on the top is? GD, the answer is B, GDHA. So no doubt the total head available is H here, and the area you need to consider the capital A. So H and A is also correct, and this D is density. This D is density, not the depth here. So you need to follow the notation given in the question. So density is D. Normally you can use rho, etc., but he has given D. So density. So this is WAH. The force needed is WAH bar. So W here. W means rho D and area, and H is H here. That is the force H here. So this value is H here. So the answer is B. So GDHA. So this is W, A, H here, and W in place of W, GD, and A is capital A here, and H is the capital H here. So the answer is B. One more question. A floating body with a center of gravity G and center of buoyancy B and meta center M. So in general, this is the specific gravity coefficient. The center of gravity coefficient. This is buoyancy and meta center. When it is floating, when any body is floating, this should be the normal coefficient. So meta center is always above center of gravity, and center of gravity always above buoyancy. So MGB. So this is specific gravity, this is buoyancy, and specific gravity is above buoyancy, and meta center is above specific gravity. So the answer is D. So G lies below M. Shear stress develops on a fluid element if the fluid is Straight away, not necessary explanation, straight away can give. It is viscous and the flow is non-uniform. Shear stress develops only when it is viscous. So the shear stress is mu into dV by dx. Without mu, we cannot expect any shear stress. When mu is equal to 0, the shear stress is 0. So this is the answer is viscous. And the flow is not necessary to have a more time for this. So 2 is D answer. So shear stress exists only if it is viscous. Fluid in motion, pressure at a point is same in all directions, then the fluid is an ideal fluid. So ideal fluid we can expect such the pressure is equal in all the directions, Pascal's law. Pressure at a point is same in all the directions. That you can expect only for ideal fluid. The answer is C. In a static fluid, the pressure at a point is equal in all directions. Same question. Answer is B. Different year he has given same question. So 5. The force per unit width. The force per unit width on the rectangular door submerged the liquid of density rho, figure shown below. So the force is W or rho G AH bar or H bar is CG. Notation is different. CG, and here rho into G you can use as it is. Rho G is there in every equation, you can use as it is here. And A is the area. The area is, if it is 1 in the other direction is 1. So 1 into 1 is the area. And what is it CG? So take the vertical distance, and the angle is theta. So sin theta is equal to, the CG is somewhere here, distance is 0.5. Distance is 0.5 or 1 by 2 here, this is 1 by 2. And side vertical distance you should require. So here sin 45 is equal to x by 0.5. So that means x is equal to 1 by 2 sin 45. And that is x bar, and this is W, and this is A. So W, A, x bar. So W is equal to rho G. So rho G is equal to 1 by 2, and this is 1, and 1 by root 2, 1 by 2, 1 by root 2. So that is equal to answer C, rho G by 2 root 2. Simple equation, W, A, x bar. So W is equal to rho G, and A is the area, x bar is CG. You can get the side distance. So sin 45 is equal to x by 0.5. Half. Which one of the following statements is true with regard to the bodies that float or submerged in bodies, submerged in liquids? The answer is D. So, for a body floating in a liquid, the stability is ensured if the center of buoyancy is below the center of gravity and metacenter is above the center of gravity and buoyancy. Very clear. So you can assure the stability when center of gravity is above buoyancy and metacenter is above center of gravity. And metacenter is above center of gravity and center of buoyancy. That is the answer here. We have discussed that earlier. The vertical gate with a base width of 2 meters and a height of 1.5 meters lies in a vertical plane. The top vertex of the gate is 1.5 meters below the surface of the tank, which contains oil of specific gravity 0.8. Consider the density of water and acceleration due to gravity to 1000 and 9.81 meters per second square respectively. The hydrostatic force exerted by the oil on the gate. Simple problem. Solution. So he has given the triangle here, and the base is 2 meters and height is 1.5, and the top is at a depth of 1.5. So the equation is again WH bar, the hydrostatic force is WX bar. So find out the area of the triangle here, half BH, so half, and B is 2 meters and H is 1.5, half BH is equal to 1.5 meter square. And the CJ here is this is 1.5 up to here 1.5. and from here to here, some students are taking h by 3. It is 2/3 h from the top, and from the bottom, the CG is h by 3. From the bottom, the CG is h by 3. From the top, it is 2/3 h. From the bottom, it is h by 3. From the top, it is 2/3 1.5. 2/3 1.5 is from the top, and from the bottom, it is 1.4, 1/3 1.5. So the depth of CG is equal to 1.5 plus 2 by 3 into 1.5. Depth of CG of the plane from the free surface is h bar. So this is 1.5 plus 2, most of the students are taking sometimes 1 by 3. So 1 by 3 h is from the bottom, from the top 2 by 3. That's why you need to know the center of gravity values appropriately for different surfaces here. So 1.5 plus 2/3, 1.5 is 2.5 meters. The density of the fluid, because the specific gravity is 0.8 and 1000 is for water, so the density of the fluid is 0.8 in 1000, 800 kg per meter cube. Density of the fluid, specific gravity, when specific gravity is 0.8, plus specific gravity is 0.8 is the mass density of the fluid by mass density of the water. So mass density of the water is 1000 kg per meter cube in a system, and which is multiplied by 0.8 is specific gravity of the fluid, which is equal to 800 kg per meter cube. So hydrostatic force is equal to W h bar A. So W is equal to 800 and G is 9.81, and area of the triangle is 1.5 and the CG distance is 2.5. The multiplication will be getting 29,430 and kilonewton divided by 1000, 29.43. It is between 29.43 means you can give between 29.3 to 29.5 the answer. So with this, the chapter of hydrostatic force and the pressure chapter we have discussed. And the next chapter is fluid kinematics. Next chapter is fluid kinematics. Start అయిందా లేదు చూసారు, రిజిస్టర్ వెళ్ళేదా ఇప్పుడు స్టార్ట్ అయిందా, రిజిస్టర్ ఫోన్ చేశారు కనుక్కున్నాం ఎందుకు అదే నేను అది 5 minutes అదే కనుక్కో సార్. సో దిస్ ఈజ్ అనదర్ చాప్టర్ ఫ్లూయిడ్ కైనమాటిక్స్. Fluid kinematics. What exactly mean by kinematics? So far we have discussed the fluid statics. Now it is kinematics. Kinematics and kinetics. So kinematics means study of fluids in motion. Fluid statics means study of fluids at rest. In the initial class I have discussed about the study of fluids at rest and study of fluids in motion is fluid mechanics. So kinematics is study of fluids in motion without the forces, and the kinetics. So hydrokinematics or kinematics both are same. Hydrokinematics or kinematics both are same. Similarly, kinetics or hydrokinetics both are same. So kinematics means study of fluids in motion without the forces, and study of fluids in motion with forces. Then how will you describe the methods of describing fluid motion? How will you describe the fluid motion? In simple words, you can say that the fluid kinematics is a space-time relationship. Space-time relationship. Space is distance. Space-time relationship. X, Y, Z and T. X, Y, Z is the distance coordinates, X, Y, Z are distance coordinates and T is the time. So if you take a velocity or any property, it is a function of space and time. This is the velocity. If you take a mass density, it is also a function of X, Y, Z and T. If you take a pressure, that is also a function of X, Y, Z and T. Just I have given only one property here. So velocity, V is the velocity, is a function of space and time. So this chapter, kinematics chapter, deals with space and time relationships. So then how will you describe the fluid motion? How will you describe the fluid motion? We have two systems here. One is fixed coordinate system and moving coordinate system. Fixed coordinate system means the coordinate is not moving. Moving coordinate system, the coordinate is moving, not necessary at UG level. But fixed coordinate system is the coordinate is fixed here. X, Y, Z axis is fixed here, not moving. And moving coordinate means X, Y, Z axis is also moving. So take a simple example on that. The observer, so he is observing the fluid properties or properties of the fluid for the flow of water, let us say. The observer means I mean to say a coordinate. Observer is sitting on the bank of the river, and he is observing the study of fluids. The fluid is in motion. Fluid is in motion. So he is observing the study of fluids while sitting on a bank. That means he is not moving. The observer is not moving. The observer is ideal. The observer is sitting on the bank and he is studying the movement of fluid in the moving water. So that is fixed coordinate system. The observer is not moving. So now take another one. Now the observer is moving. So when the observer is moving he is sitting in a moving boat. So the boat is moving and the fluid is also moving, the boat is also moving. So boat is moving in a flowing fluid. So the observer is sitting in a moving boat. So when the observer is sitting in a moving boat, when the fluid is moving, then you can say that it is moving coordinate system because the observer is moving. In the previous case, the observer is not moving, he is stationed, he is sitting on a bank of the river, whereas now he is moving on a moving boat, he is moving on a moving boat and the water is also flowing. So that is moving coordinate system, example for moving coordinate system. Then how will you define the velocity of the fluid particle? So suppose if you take a solid, so solid measure the velocity of the body as a whole. Solid measure the velocity of the body as a whole. Whereas if you take a fluid means it consists of number of fluid particles. Fluid means it consists of number of fluid particles. It consists of number of fluid particles. When the fluid particles are more, each particle will have instantaneous value of velocity, pressure and density. So the fluid particles are different. The fluid particles are different. Each particle will have its own value of pressure, density and velocity. So then how will you define the velocity of the fluid particle? So no doubt any velocity is displacement by time. If it is solid, distance moved by solid particle per time, displacement by time. So whereas in the fluid, I have not given here, so the velocity is equal to distance moved by the particle in time dt, as latter tends to 0, limit dt tends to 0. So here we have a limit dt tends to 0, ds by dt. So the velocity of the fluid particle is equal to ds by dt. Limit dt tends to 0. This is the definition of fluid velocity. If you take a solid velocity, it is simply displacement by time. Fluid velocity, because the velocity is not a whole. Velocity means, fluid means it is not a single fluid, group of fluid elements. Each fluid element will have its value of velocity, pressure, density, and we can define the fluid velocity as distance moved by fluid particle in a time dt, as latter tends to 0. That means the fluid velocity here is limit dt tends to 0, ds by dt. Now if you resolve this velocity v into three components in the direction of x, y, z. So we have x, y, z axis, and resolving v into u, v, w. So సార్ రిజిస్టర్ గారు సార్ కనపడు సార్ వెళ్తానంటే నేను వచ్చేస్తాను, వచ్చి 5 నిమిషాలు వస్తాను క్లాస్ సార్ కనపడి చెప్పు 10 నిమిషాలు ఉంటే 10 నిమిషాలు ఆగి చెప్తాను కనపడి చెప్పు. సో ది వెలాసిటీ హియర్, fluid velocity here, the v can be resolved into three directions: small u, small v, and small w. V is equal to, we can resolve v into three components. So component of velocity in the x direction is small u, component of velocity in the y direction is small v, and the component of velocity in z direction is small w, u, v, w. So the velocity can be resolved into three directions. So the velocity in the x direction is small u, velocity in the y direction is small v, velocity in z direction is small w. Similarly, resolve ds into three directions. So distance ds in the x direction is dx, ds in the y direction is dy, ds in the z direction is dz. That means we have resolved v into u, v, w, x, y, z directions, and resolve ds in three directions x, y, z. Then this small u is the velocity component in the x direction. Why I am stressing this is we will be getting this in future for subsequent chapters also. The small u, small v, small w, capital, etc. So small u is the velocity component in the x direction. Small u is the velocity component in the x direction. So then what is distance traveled in the x direction? So distance traveled in the x direction dx, and the time is dt. So the velocity component in the x direction is equal to distance traveled in the same x direction by dt as dt tends to 0. So limit dt tends to 0, limit dt tends to 0 dx by dt, limit dt tends to 0. Similarly, limit dt tends to 0. Suppose if you take v, the velocity component in the y direction, small v means the velocity component in the y direction. Small v is the velocity component in the y direction. So which is equal to limit dt tends to 0, limit dt tends to 0 dy by dt. So what is this dy? Distance moved by the particle in the y direction. This is time. And w is, what is w? W is the velocity component in the z direction. So find out the distance traveled in z direction by time. So distance traveled by z direction by time. So limit dt tends to 0, dz by dt is w, velocity component in the z direction. This is very, very important. We will be getting this quite often in the derivations and also in the subsequent chapters. So fluid velocity is limit dt tends to 0 ds by dt. The velocity component in the x direction is limit dt tends to 0 dx by dt. The velocity component in the y direction is limit dt tends to 0 dy by dt. The velocity component in the z direction is w, which is equal to limit dt tends to 0 dz by dt. Remember this, and which will be useful here. Then classification of flow. Classification of flow. We have a steady and unsteady flow. We have steady and unsteady flow. What is meant by steady flow and what is meant by unsteady flow? The steady flow is so the fluid velocity, steady flow. See all the properties, considered velocity, mass density, pressure, etc. So all the properties where they do not change with time, all the fluid properties when they, this is also very, very important. Quite often we will getting assume the flow as steady, assume the flow as uniform, assume the flow as compressible, something like that. So if all the fluids, if all the properties, that is pressure, mass density, velocity, all the properties are when they do not change with time, you can say it is steady flow. So that means, for example, you take velocity here, and the velocity is not changing with time. So the velocity change, differentiation of velocity with reference to time. వచ్చేసి ఒక క్లాస్ ఉన్నాను కదా 5 minutes break లో మళ్ళీ అనుకో వచ్చేస్తా నేను వచ్చేసి. So the velocity change of velocity by time. Suppose if you take a steady flow as all the fluid properties, if all the fluid properties or when they do not change with time, you can say it is steady flow. Suppose if you take a velocity, just an example I am taking here, just a velocity, and if v is constant with time, so dv by dt is 0. As the velocity is not changing with time, dv by dt is equal to 0. So any property with reference to time is 0. If you take a derivation, that is steady flow. Unsteady flow means when the properties, when they change with time, any one property or all the properties, when they change with time, you can say it is unsteady flow. Just opposite that. So as it is not constant with time, dv by dt is not equal to 0 for unsteady flow. The change of velocity time not equal to 0, so it is unsteady flow. Similarly, uniform and non-uniform flow. So uniform and non-uniform flow is when the fluid velocity, the uniform flow always refers to the distance at a particular time. Steady flow is always refers to time for all the properties. Uniform, non-uniform means it is only for the velocity. Uniform velocity or non-uniform velocity or uniform flow is for velocity only. And whereas steady and unsteady means all the properties. Consider all the properties here. All the properties when they do not change with time, it is steady. When the fluid velocity, if it doesn't change with the distance at a particular time, it is uniform flow. So the uniform flow, the velocity is not changing with distance at a particular time. So this is velocity with change of time. This is velocity with change of distance. So at that particular time, the time is constant now. The velocity is, if it not changes with distance, then it is uniform flow. So dv by ds is equal to 0. So because it is constant with the distance here, so dv by ds is equal to 0. Differentiation will be 0. Constant is 0. And if it is a non-uniform, just opposite that, if the velocity changes from place to place at a particular time, then it is non-uniform flow. So that means dv by ds, as it is not constant, it is not equal to 0. So dv by ds value existing. So that's why it is dv by ds is equal to not equal to 0 for non-uniform flow. Take a simple example. Steady uniform flow. If the flow is steady and also uniform flow, you can take that steady through a long pipe at constant diameter and a constant rate. Example for steady uniform flow is flow of a liquid through a pipe. The diameter is constant and rate is also constant. Discharge is also constant. You can get a steady uniform flow only. Consider the flow through long pipe. The pipe diameter is constant and the rate of flow is also constant. That is a steady uniform flow. For example, take unsteady non-uniform flow. The flow is not steady, the flow is not uniform. So that you can expect when the flow through a pipe, the pipe is tapering, the diameter is not constant and the rate is also varying, the discharge is also varying. So that is unsteady non-uniform flow. Examples you need to remember, you need to write, normally asking in the objective questions. For example, steady non-uniform flow. So the pipe of different diameters at a constant rate. Study non-uniform flow. When the flow is constant, when the flow rate is constant, you can take a steady flow. When the pipe diameter is same, we can take uniform flow. So when it is steady non-uniform flow, it is a pipe of different diameter, tapping pipe at a constant rate. Then what is 3-dimensional, 2-dimensional and 1-dimensional flow? 3-dimensional, 2-dimensional, 1-dimensional flow. Name is very clear. It is a 3-dimensional flow. So 3-dimensional flow is the flow which is occurring in all the 3 directions. For example, if you take velocity, velocity is a function of x, y, z and t. So it varies all the 3 directions, x, y, z, x, y, z, 3 directions. So when any property varies in all the 3 directions, x, y, z and also time, it is a 3-dimensional flow. And suppose if you assume the fluid as steady, 3-dimensional steady flow. So steady flow means with the time it is constant. So 3-dimensional steady flow is take velocity, the function of x, y, z, no t. And 3-dimensional unsteady flow, and it is also varying with time. Then you can take 3D flow is velocity, take any property, is a function of x, y, z and t. So 3-dimensional unsteady flow is x, y, z, t. 3-dimensional flow is a function of x, y, z. Similarly, 2-dimensional flow. The flow varies only in 2 directions. So function of x, y. The flow varies only in 2 directions, function of x, y. 2-dimensional unsteady flow, function of x, y, t. 2-dimensional steady flow, function of x, y. Similarly, 1 dimension. So the flow varies only in 1 direction. The velocity, any property, is a function of x only. Function of x and t, if it is unsteady flow. The velocity is a function of x and t for 1-dimensional flow. And the velocity is a function of x only for 1-dimensional steady flow. Then what is rotational and irrotational flow? What is rotational and irrotational flow? So rotational flow, a flow is said to be rotational if it rotates about its mass center while moving in the direction of flow. Rotational flow is the flow while moving the fluid, when it rotates about mass center, you can say it is rotational flow. You can take the example, liquid in the rotating tank. We can take the example, liquid in the rotating tank is rotational flow. Rotational flow means if the fluid, while moving in the direction, if it rotates about its mass center, we can say it is a rotational flow. Irrotational flow. So when it do not rotate about its mass center while moving the direction, you can say that it is irrotational flow. Irrotational flow. So irrotational flow is equal to irrotational flow. The example of irrotational flow is ideal fluid. Example of irrotational flow is ideal fluid. Similarly, rotational irrotational flow. Yeah, so we'll take a short break and again I will come back in 5 minutes. So now the time is 10:40. So I'll come back in 10 minutes and we'll start the class again from 10 to 12. We'll have a break and we'll take water and refresh and come back at 10 minutes. Gate online classes kada motham the entire state voice agastante meeku over
ఎలా సార్ అంటే 50 దాటుతారంటే 25 It's fun.
So yes, sorry for the slight delay. So we are discussing various types of flows. We have discussed the steady and unsteady flow, uniform, non-uniform flow, 3-dimensional, 2-dimensional, 1-dimensional flow, rotational and irrotational flow. Next one is laminar and turbulent flow. So if the fluid flows such a way that each and every particle flows smoothly, the fluid flows smoothly, steadily, without any irregularities, without intermingling of the fluid particles. When the flow flows steadily with stability, no mixing, no intermixing, no disturbance, no eddies, then you can say it is laminar flow. Then the other one is turbulent flow. Name itself very clear, turbulent. When the fluid flow, while moving, when there are irregularities, erratic motion, eddy formation, intermingling of the fluid particles, all sort of disturbance, speed flow, erratic flow, irregular, and you can expect flow in reverse, etc. Highly irregular, erratic, and intermixing of particles, this side and that side, top to bottom and bottom to top, etc. That you can say is a turbulent flow. Then streamline, path line, and streak line. Streamline, path line, and streak line. Streamline is the line which is drawn through a flowing fluid. Streamline is a line which is drawn through a flowing fluid such a way that if you take a point on a streamline and draw a tangent, so that gives a direction of velocity of the fluid particle. Streamline is a line in a fluid flow on a streamline. If you take a point on a streamline and draw a tangent, that gives a direction of velocity of a fluid particle at that instance of time. In other words, you can give that it gives a direction of velocity of number of fluid particles at a particular time. Streamline gives directions of velocities of number of fluid particles at a particular time. Any point on a streamline, if you draw a tangent, that gives the direction of velocity. Similarly, path line. Path line is a line traced by a single fluid particle over a period of time. Path line is a line traced by a single fluid particle over a period of time. Now the time is not constant. With the variation of the time, if you consider the path by the single fluid particle, then it is a path line. Path line, very clear. In other words, it gives the direction of a single fluid particle over a period of time. So here the particle is single, the time is variable for the flow line. Path line. For the streamline, we have more number of particles and directions are more and the time is constant there. Time is variable here, path line, and time is constant in streamline. Difference streamline path line is also important. A streak line. When a dye means when a color solution, so there is some flow, a pipeline, there is some flow, and inject some color solution. The path followed by color is a streak line. Streak line. Streak name itself is very clear. Streak line means if you have a pipe flow, and a color solution is injected in the pipe flow and the path followed by color solution is called streak line. Streamline, path line, streak line are very, very important. Stream tube. Stream tube is imagined to be formed by a group of streamlines. So we have a number of streamlines, and the stream tube is a group of streamlines in an enclosed curve consisting of number of streamlines. Because the point selected on the streamline, if you draw a tangent that gives the direction of velocity, and there is no normal component to the velocity, there is no flow across the streamline. There is no flow across the streamline, as stream tube is also having number of streamlines. There is no flow across the stream tube. So you can consider only in one direction. If you take up the problem for the stream tube, you can consider only one direction. If you take up the problem in XYZ directions, that is three-dimensional. Suppose if you assume if you consider that derivation for a stream tube, you can consider only one direction because there is no normal direction for the stream tube. The fluid enters the tangential direction and leaves in the tangential direction. That is the advantage of stream tube. You can simplify the derivation if you consider the derivation on a stream tube. So stream tube, imagine to be formed a group of streamlines in a small enclosed curve. And you can clearly note that there is no flow across the streamline. There is no flow across the streamline or stream tube because if you draw a tangent that gives the direction of velocity, you don't have any normal component in that, so there is no flow across the streamline. And stream filament. A stream filament, you can say that stream tube with a small cross-section area. Stream filament is also a stream tube with a small cross-section area in which the variation of the velocity is negligible. You can say it is stream filament. Stream filament is stream tube with cross-section area small enough for the variation of velocity is negligible. Stream tube, a small area in which the variation of velocity is negligible. So it is called stream filament. Important object type. Stream tube with cross-section area small enough for the variation of velocity or it is negligible, you can call it as a stream filament. Then three-dimensional continuity equation. So it is based on law of conservation of mass. It is based on law of conservation of mass. What it says? Mass can be neither created nor destroyed. Law of conservation of mass. Mass can neither be created nor destroyed. Suppose if you take a fixed region, take the equation that inflow means the rate at which the fluid mass enters the region. Inflow, the fluid is entering. The rate at which the fluid is entering. So that means mass per second which is entering the region per second, mass per second entering the region is inflow. Outflow, the mass per second which is leaving the region is outflow. Inflow, the fluid is entering, mass entering per second, rate of mass, outflow, rate of mass leaving. Inflow minus outflow is equal to what could be the change in the fluid mass? In other words, rate of increase of fluid mass. So rate of increase of fluid mass is equal to inflow minus outflow, law of conservation of mass for steady flow, because you are considering inflow means mass per second entering, mass per second leaving, and increase of fluid mass per second. Everything is in terms of time. For steady flow means when they do not change the properties with time, you can say steady flow. So as there is no change with reference to time, for steady flow, inflow is equal to outflow. Inflow is equal to outflow. Then continued equation. Three-dimensional continued equation. Suppose if you see here, 6 phases. So this is dx, one side, and this is dz, and this is dy. dy, dx, dz. Suppose if you take the center point here, the mass density is rho, and the velocity is capital V. So velocity we have in 3 directions: x direction small u, y direction small v, and z direction small w. Small u is the velocity component in the x direction. Small v is the velocity component in the y direction. Small w velocity component in the z direction. Then rho into velocity into area is mass per second. So mass density, mass per second is mass is equal to mass density into volume, and mass per second is mass density into volume per second. So that means rho into area into velocity is mass per second. Mass density into area into velocity is mass per second. So take x direction. Only I will consider only one direction. So take x direction. X direction, because the flow is normal to surface of flow, so x direction we can consider only 2 phases. I mean, one phase is ABCD. This is one phase in which water is entering in x direction. The other phase which is leaving, A, D, B, C dash, the phase in which the water is leaving. So this is the inflow x direction you can consider the phase ABCD. Inflow, outflow x direction you can consider the phase A dash, B dash, C dash, D dash. That means for x direction you need to consider inflow ABCD, outflow A dash, B dash, C dash, D dash. So then mass of the fluid exactly at the center, is equal to mass density, velocity is small u because we are taking the x direction, and the area is d by dz. And area, this is dz and this is dy. So acceleration we need to consider only this area. Acceleration only this area. So mass density into velocity into area. Area, because we are taking the acceleration we have this one, dy dz. So rho into dy dz is mass per second at the center. Then find out at inflow. So inflow is equal to, so we have the value here, this value. So rho by dy dz, while we are moving this direction, let us say minus sign. So we have the mass here, we are finding the mass per second here, and we are finding the mass per second here. When you move towards left side, towards negative x-axis, take negative sign here and take positive sign here. So the mass here, mass of the phase ABCD, mass inflow through the phase ABCD is mass per second at the center, rho u dy dz. Sign is negative. So take negative sign, and change of mass with reference to distance. Change of mass is d by minus d by dx, because we are taking dx, and the mass is rho u d by dz. Rho u, this is the mass here. So inflow is equal to rho u d by dz minus, why it is minus? Because you are moving from here to here. We know here the value, but we want to get the value here. So rho u dy dz minus d by dx of rho u dy dz, and the distance from here to here. Distance from here to here is dx by 2. Total is dx, and distance from here to here is dx by 2. That is the equation. And same procedure is there for each and every derivation. Sometimes you may ask a small derivation, so that's why I am stressing this. Similarly, that is inflow, and if you take outflow, so outflow is equal to, we have the mass here, rho u dy dz, and when we are moving toward this side, add positive sign, so rho u dy dz plus d of this mass by dx, and the distance from here to here is again dx by 2. So outflow is equal to rho u dy dz plus d of rho u dy dz by dx into distance is dx by 2. From here to here dx by 2. That is inflow and this is outflow. Inflow minus outflow, and steady flow inflow is equal to outflow. So based on that, he has derived an expression for three-dimensional continuity equation. Three-dimensional continuity equation. The assumptions are steady flow, the flow is steady, any property they do not change with time, and the fluid is uniform, and the fluid is incompressible. Incompressible means mass density is constant. Incompressible flow, mass density, mass per volume is constant. It is not compressing. Whatever the compression, we have the same volume. Same mass in a given volume. So the mass density is constant. That is incompressible flow, and steady flow, and in steady, uniform, and these are the assumptions for continuity equation. Three-dimensional continuity equation is. The assumptions are asking steady, uniform, and incompressible are the assumptions for three-dimensional continuity equation. For steady flow, inflow is equal to outflow. Again, the equation is du by dx plus dv by dy plus dw by dz. So what are the small u, v, and w? So this is a three-dimensional continuity equation for a steady, uniform, incompressible flow. So small u, small v, and small w are the velocity components in x, y, and z direction. So du by dx plus dv by dy plus dw dz is equal to 0. Velocity component in x direction, velocity component in y direction, and z direction. Then suppose if you reduce this three-dimensional continuity equation to the two-dimensional case, then what is the change in this equation? If it is a two-dimensional continuity equation, then this is du by dx is equal to dv by dy is equal to 0. dv by dx plus dv by dy is equal to 0. If it is a one-dimensional continuity equation, then what is the change? So du by dx is equal to 0. So because the other two dimensions there is no variation, so du by dx is equal to 0 for one-dimensional continuity equation. Two-dimensional, du by dx plus dv by dy is equal to 0. Then there is another continuity equation, this is also called continuity equation, which involves cross-section area. Again, the assumptions are same, steady, uniform, and incompressible fluid, the assumptions are same. And this is continuity equation which is involving cross-section area. This equation which is not involving cross-section area. Suppose if you take one-dimensional continuity equation which doesn't involve cross-section area, du by dx is equal to 0. Which involves cross-section area is q is equal to a1 v1 is equal to a2 v2 equal to a3 v3. So continuity equation involving cross-section area for steady, uniform, and incompressible flow is equal to, so that defines that the quantity of water which is flowing through the pipe is same. Q is the discharge. So discharge is volume per second. Discharge is volume per second. And A1 is the area. And V1 is the velocity. A2 is the area. And V2 is the velocity at section 1, section 2, section 3. The quantity of water flowing through the pipe is same. Q is equal to A1 V1 is equal to A2 V2 is equal to A3 V3. So the quantity of water flowing through the pipe is same. A1 is the area at section 1, V1 is the velocity at section 1, A2 is the area at section 2, V2 is the velocity at section 2, and A3 is the area at section 3, V3 is the velocity at section 3. A simple procedure again. For finding out the one-dimensional continuity equation, we'll be using steam tube. So I told you steam tube is a group of streamlines which are enclosed in a small curve, Take any point on a streamline, and if you draw a tangent, that gives the direction of velocity. That means if you take a streamline, the entire equations we can consider only in tangential direction because there is no normal flow. So the flow is from tangential direction. This is inflow and this is outflow. If you draw a tangent and as there is no normal component, so there is no flow across a stream tube, no flow across a streamline. So we can we can simplify this for tangential direction, only single direction. Same equation, inflow minus outflow. So here again mass density into area into velocity. The mass per second at the center is mass density into area into velocity. The cross section area is A and V is the velocity rho A B. And suppose you want to find out inflow. So inflow is equal to, we have the value, known value here, rho A B, because you are moving towards the negative side. So the sign should be negative. And the change of mass. So change of mass is D and mass is dAV, with reference to distance is dx. So ds. So d by ds into rho AB, and the distance from here to here total is ds, and the distance from here to here is ds by 2. So this is the mass here at the center. We find out the mass of the second entering here is equal to mass per second minus, because you are moving towards the negative side, minus, and the distance is ds here, d by ds, and again this is mass here, change of mass here when you are moving from here to here, and the distance here is from here to here is ds by 2, simple equation. So if you know this equation, how to write this equation, you can derive any number of equations in fluid mechanics. Again from here to here, this is inflow and this is outflow. So outflow is equal to, the mass at the center is rho AB. We have the properties here, mass density, velocity here, the values are here, and mass density into area into velocity. This plus, the sign is positive because this is moving towards, so this is moving towards positive x-axis. This is moving towards positive axis here. So d by ds, why it is positive? Because we are moving positive towards positive. This is negative, we are moving towards negative. So plus d by ds into rho AB, d by ds rho AB into ds by 2. D by ds rho AB into ds by 2. ds by 2 is the distance from here to here. Half of the distance here. So then the equation is, suppose if you use the streamline equation, the continuous equation involving cross section area is equal to Q is equal to A1 V1 is equal to A2 V2 is equal to A3 V3. So these two equations are very important, and we have number of problems on these equations. Definitely we have questions on gate examinations. Then the other one is acceleration. Acceleration. What is acceleration? Acceleration is rate of change of velocity. Acceleration is rate of change of velocity. So acceleration in the x direction is equal to, acceleration is rate of change of velocity. Suppose take acceleration in the x direction ax, take acceleration in the y direction ay, and take acceleration in the z direction az. So ax is equal to change of velocity with time in the x direction. Ay, change of velocity in the y direction to time. So this is v, not y here, sorry, this is v. So change of velocity in the x direction, is du, and one minute. A. So 1 minute. change of velocity in the x direction is du by dt. So change of velocity in the x direction by time, and time tends to 0, limit dt tends to 0. And change of velocity in the y direction is dv. So dv by dt. So limit dt tends to 0, dv by dt is acceleration in the y direction. And change of velocity in the z direction, acceleration in the z direction. Acceleration in the x direction is change of velocity du in the x direction by time. Change of velocity in the y direction by time. Limit dt tends to 0, limit dt tends to 0. And az, the change of acceleration in the z direction. So limit dt tends to 0, limit dt tends to 0, dw by dt. dw by dt, that is a change of velocity in the z direction by time. Limit dt tends to 0. And other acceleration. So you can expand acceleration ax, ay, az. I have taken ax here for our notice. So ax is equal to small u, velocity component in x direction, du by dx, small b, du by dy, small w, du by dz plus d by dt. So here, if you see here, change of velocity with reference to direction x, y and z, and this is the change of velocity with reference to time. Change of velocity with reference to x direction, change of velocity with reference to x direction, and change of velocity with reference to y direction. So here, if you see here, ax, so this is the change of velocity, x direction, y direction here, and z direction here with reference to distance, and this is the change of velocity with reference to time. So why I am stressing here is there are two types of acceleration. So one is changing velocity with reference to distance, another one is changing velocity with reference to time. Then there are two types of acceleration. One is the local acceleration, another one is convective acceleration. One is the local acceleration, another one is convective acceleration. So if the velocity changes the time, you can say it is a local acceleration. So the acceleration we have two times here. One is the velocity change with reference to distance. The other one is velocity change with reference to time. So when you mention the change in velocity with time, you can say it is local acceleration. Then the important objective type is for which type of flow local acceleration is 0. Steady flow. So for the steady flow, any property with reference to time is constant. Any property with reference to time is constant. So for the steady flow, local acceleration is 0. For steady flow, local acceleration is 0. Similarly, convective acceleration. Convective acceleration is acceleration in which we consider the change of velocity with reference to distance. Change of velocity with reference to distance. Then the example for local acceleration is du by dt. The example for convective acceleration is this one. Du by this, du by this is the example for convective acceleration. This is the example for local acceleration. So local acceleration is 0 for steady flow, and convective acceleration is 0 for uniform flow. Uniform flow always velocity with reference to distance. Uniform flow means the fluid velocity doesn't change the distance at a particular time. Very, very important for object type. Local acceleration is 0 for steady flow. Convective acceleration is 0 for uniform flow. So local acceleration, velocity change time. Convective acceleration, velocity change the distance. Then tangential and normal acceleration. If you consider the velocity in the tangential direction, consider the velocity in the normal direction, consider acceleration in the tangential direction, and consider acceleration in the normal direction. So velocity in the tangential direction, so distance moved by the particle in a time is ds. So ds by dt is the velocity in the tangential direction, limit dt tends to 0. And velocity in the normal direction, so limit dt tends to 0, dn by dt. And acceleration in the s direction, so change of velocity in the tangential direction by time, limit dt tends to 0. See exactly similarly, small u, small v, small w, ax, ay, az in the xyz direction. Similarly, tangential normal direction, only same values. So Vs is equal to ds by dt, and As is the acceleration in the tangential direction dvs by dt, change of velocity with reference to time, and Vn is equal to dn by dt, change of distance in the normal direction by time, limit dt tends to 0, and An is the acceleration in the normal direction, change of velocity in the normal direction by time, change of velocity in the normal direction by time, so limit dt tends to 0. And similarly, like Ax also can write Vs dvs by ds, Vn dvs by dn plus dvs by dt. So here also you can give the steady flow. I mean local and convective acceleration. So local acceleration is once again here also we can represent the change of velocity with the time is local acceleration. Change of velocity with time is local acceleration, and change of velocity with the distance is convective acceleration. So this is the example for convective acceleration, and this is the example for local acceleration, dvs by dt, local acceleration, convective acceleration, this is the convective acceleration. Then local acceleration, this is example, this is 0 for steady flow, steady means with reference to time, and this is 0 for uniform flow. So convective acceleration is 0 for uniform flow, local acceleration 0 for steady flow. And the other one is rotational and irrotational flow, rotational and irrotational flow. So rotational and irrotational flow, earlier I have discussed, if the fluid particles while moving in the direction, if they rotate about mass center, you can say it is a rotational flow. When the fluid flow, when it rotates about, when they do not rotate about mass center, we can say it is irrotational flow. We can say it is irrotational flow. Rotational flow and irrotational flow. Rotational flow is the flow when the fluid particles, when they rotate about mass center, when they rotate about mass center, you can say it is rotational flow, and fluid is rotating tank. And when the fluid, when they do not rotate about mass center, then it is irrotational flow. Irrotational flow. Example is ideal free. So you have a rotation component here, Wz. So Wz is equal to 1 by 2 dv by dx minus dv by dy. So see here, v is the velocity component in the y direction, dv by dx. This is the velocity component in the x direction, dv by dy. If it is equal to 0, you can say that it is irrotational flow. If it is equal to 0, then you can say that it is irrotational flow. Okay, student friends, this is also very, very important chapter for GATE examinations. And I will continue tomorrow the balance, and we will try to take up the objective questions also tomorrow for fluid kinematics. Almost a maximum portion of the content is completed, fluid kinetics or fluid kinematics. And please, have a grip over that. So I have mentioned different types of flow. I have mentioned velocity, acceleration, different directions, tangential velocity, normal velocity, accelerations, streamline, path line, streak line, laminar flow, turbulent flow. A lot of terminology has introduced up to now. So please be focused on that and try to prepare all these things, and so that it will be easy for you to understand the subsequent topics in this chapter, and also the problems and the objective questions tomorrow thereon. So I'll be taking tomorrow class Sunday at 10:30 same time, and have a comfortable time, and please prepare these fundamentals and these notations, etc., so that tomorrow we'll complete this chapter, fluid dynamics, and start fluid dynamics also, depends on the time. And thank you very much for your patient hearing, and thank you. We'll meet tomorrow.